Okay, we'll go from current slide. Any questions on anything we've done up till now? I was going to make this announcement when more people got here, but I'm afraid if I don't, I'll forget about it. So if they do listen up on their things, they'll hear about it. Next week, we've got one of those good news, bad news situations coming up. The good news is Monday is a holiday. It's Labor Day, so the day's off. The bad news is we won't be meeting. Sorry about that. So you'll have to get over it. We'll only meet one time next week, 1 week from today. Okay. Any questions on anything we've done so far? Okay. Where we left off last time, if there are no questions, in Chapter 7, Applications of Integration, Section 7.1, Areas of a Region Between Two Curves, this last little segment here is called Integration as an Accumulation Process. And this does sort of, it's true, it makes sense. I really don't see a big point in going over it, but the book does, so we will. Okay? The integration formula for the area between two curves was developed by using a rectangle as a representative element. For each new application of integration in the remaining sections of this chapter, which we'll have plenty, an appropriate representative element will be constructed using pre-calculus formulas you already know. Sure you do. I mean, of course you do. Each integration formula will then be obtained by summing or accumulating these representative elements. So basically, what we'll do, we'll start with some known formula. Now, whether it was something you knew in pre-calculus or not, I don't know, but some formula that makes sense, describes something physically. We'll start with that, then use that to represent in some representative element, some little rectangle, and then come up with a new integration formula. That will be basically the approach. Okay? For example, the area formula in this section was developed as follows. The area is the height times the width. Okay, the height turned out being the difference between f and g of x when we were doing a vertically, vertical rectangle, and the width was your delta x. So that delta a is what we're integrating over, and we're letting the delta. So your total integral a, the total area a, will be the integral or the summation of all these height times width of all those rectangles from A to B. Okay, that's what we did. Nothing too magical about it, but it makes pretty good sense. Hopefully it does to you. Okay, now here's example 6. Find the area of the region bounded by the graph y is equal to 4 minus x squared and the x-axis. Going back to a simple type 1. Okay? Describe the integration as an accumulation process. So, all that talking they did, they really didn't do much as far as accumulation process. Now, and I'll let their illustration follow. Let's just do what it says. Find the area of a region bounded by the graph of y is equal to 4 minus x squared and the x-axis. Now, I'm assuming, well, okay. What do we need to do that? What pieces of information do we need to know? Second? Okay. F of x, I'm going to assume right now off the top will be the y. Let me get my pen set up. Okay. I'm going to assume this will be my f of x. I may be wrong on it, but I believe that'll be a pretty good one. And then the g of x, what's that going to be? You need some y for that. What are we going from this to the x-axis? What equation might you have there? It's true about the x-axis. There is an equation, y equals 0, and that would be your g of x. Okay? Pretty easy one, right? Okay, so there's your f and g. Got it? I can even do that subtraction fairly easily without your help, but maybe I might need your help. Okay. Next.
Integration.
What?
We make an integration.
The integration, okay. What will that integration be? A is equal to? Any help?
-2 to 2.
How did you get that? Okay. Yeah, that's exactly right. Good choice. But what you really were doing, you set this function equal to this function. Remember? So you set 4 minus x squared equal to 0. And then you factored and, unfold it, whatever you want to call it, and you got that to be 2 minus x times 2 plus x, that's an x there, is equal to 0. And what did that give us? I think what you just said, x equal 2 and x equal -2. So that's a good choice to go. Your integration is going to go from -2 to 2 of what? G of x, and I can do that subtraction. That would be 4 minus x squared minus 0, done. And then dx. Now I know that's what they want me to use, okay, because they said find the area and then describe that integration as an accumulation process. But I'm a little lazier than that, okay, because what can you notice about this function? This thing that you're integrating. Anything special about that function?
It's a parabola.
It's a parabola. Going down. Very good. Anything else?
4 spaces up.
It's what?
4 spaces up.
4 spaces up. And where is that 4 spaces up located?
The y-axis.
On the y-axis. And then it goes down evenly from that. So what do you call that?
Parabola.
Yes. What kind of a function though? This as opposed to that. This as opposed to that. An even function, right? Now what is it about integrating even function over a symmetric interval? I kind of don't like drawing graphs. This one's worth it. Okay, you've already described it to me really well. Okay. Okay. Said it starts at 0, 4, and we know it has intercepts at -2, 0, and +2, 0. And as you said, it's a parabola with that as the vertex. There we have it. So guess what, folks? Now, even in my ugly drawing, which doesn't look quite right, isn't this area look like it should be just about the same as that area? If it's a parabola, it's symmetric, right? About the, what do we call that? The line of symmetry, axis of symmetry. It happens to be with y-axis. So how might I more easily do this problem? That part stays the same. But how could I more easily do this problem?
-2 to 0.
Say again?
-2 to 0.
You could do that if you like negative numbers that well.
0 to 2.
Or 0 to 2. I'm lazy enough to not like negative numbers that well. But what you got to do if you do that?
Multiply by 1/2.
No, the other way. You're doubling it. This will be the area here, right? And to get the whole area and the whole thing, you have to double that. So that's what we do. Okay? This is sort of messing up their accumulation process, but it still works. We'll get there. Okay? So this will be 2 times, can we do the antiderivative of 4 minus x squared? Anybody? 4x minus x cubed over 3, evaluated between 0 and 2. Can anyone see why I didn't want to use the negative 2 in there? It's far easier to evaluate it at 0, isn't it? Okay? 2. Now, let's plug in 2, and what do you get? Anybody? 8 minus 8/3. I'll do the 0 part. Okay, done. Okay. Now, there's a couple ways you can proceed here. How would you like to proceed? The rest is just mathematics. It's not even algebra. It's just math. How would you get, what would you do from there? Well, you'd get more people here, wouldn't you? The swimmer arrives, okay. Dawson's here. The other swimmer coming? Okay, good. Harder paddling today, wasn't it? Okay. We're on page 449. This is Chapter 7, Applications of Integration, 7.1, Area of a Region Between Two Curves, and we're doing integration as an accumulation process. But basically, we're just doing an integration problem, which we've gone this far on. How would you proceed from there?
I changed the 8 to 24/3.
I like that idea. Multiply numerator by 3 and denominator, which is a 1, by 3. And that gives you 24/3 minus 8/3 would be
16.
And then double that and you get 32/3. Okay? That's the area under the curve. Okay? Now, there's finally they give the answer. 32/3. Now, what they wanted you to do was imagine, and well, okay, hold off on that. That's what we did. Let's see how they did it, because they did do it, and now you'll see what they're talking about with an accumulation process. Okay? We'll erase. Any questions for our erase these? We got 32/3, and they got it. I've got to find it again. There we go. All right. The area of the region, just as you said, and they did it from minus 2 to 2 of this thing minus 0, which is that thing. They didn't tell you how they got to minus 2 to 2, but you found it. You set one curve equal to the other curve and found the points of intersection plus x equal plus 2 or minus 2. So those became your limits. The height was the first curve, minus 0 the second curve, and your dx was the width. Now, you can think of integration as an accumulation of the areas of the rectangles formed as the representative rectangle slides from x equal minus 2 to x equal 2, as shown in this figure. Now, of course, this is how I thought about it. Right. Okay? But you start with this, and then you draw a little rectangle, okay, and let that move along here. And they did it from 0 to minus 2 to minus 1, and you covered that area. then you let it go on to 0 and you cover that area, let it go on to 1 and you cover that area, and finally you stop when it gets to 2. So you're accumulating those areas as you go. Now, we didn't quite do it that way because Ryan wasn't here, but he is now, so we'll go back and explain. What we were doing was just doing 0 to 2, but every time you did this, we were doubling, so you were then accumulating going this way from the origin, from the y-axis to plus or minus 2, because we were doubling. We got this area, but doubled it, this area doubled it, so finally we have the whole area there. Do I ever sit down and think of this as an accumulation process? Very seldom, okay? I don't even see why you would want to do that, but that is indeed what's happening. There may be some problems that this is exactly how you think of it, okay? I just can't think of what they are right now. Though I can probably think of some. If you think of, this is sort of a bizarre problem, but you run into it in some things like physics and stuff. If you think of perhaps lowering a rope, okay? The more rope you lower, the more weight is pulling down, okay? If it's supported up here, but you're lowering it through a hole there, the first part, it goes pretty easily, but then after a while, you almost have to hold back on the rope because you have so much weight pulling it downward. That is sort of an accumulation process, okay? Josh, right? Huh?
Yes, sir.
Okay. What, you sprained your ankle swimming?
No, not swimming. Swimming basketball.
Oh, I see. Okay. I was wondering how you did that, but okay. That makes more sense. Okay. So, we have a friend who, almost like a goddaughter, and she is a great swimmer. But she has had more accidents swimming than you could imagine. And you would think, how do you do that? But she is now actually a swimmer at Auburn, swimming for the swim team. They have a very good swim team. So she is really good, but she still, over the course of her growing up, has had more accidents in the pool than we thought were possible. Okay, because you think of swimming as a pretty safe sport for accidents, but so I was going to see how Josh managed to sprain an ankle swimming, but it was basketball. Okay. Any questions? So there probably are some cases that you will do accumulation. And I'm pretty sure that's the last slide. It is. Homework exercises in section 7.1 would then be any of the odds 5 through 9. They're all at Calc Chat. 7's at Calc View. Either 11 or 13, they're both at Calc Chat. 11's at Calc View. Any of the odds 15 to 27, they're all at Calc Chat. 17's at Calc View. Do 29 is both at Calc Chat and Calc View. Any of the odds 31 to 35, they're all at Calc Chat. 37 to 41, all at Calc Chat. 37's at Calc View. 43 or 45, they're both at Calc Chat. 47 or 49, both at Calc Chat. 51's a Calc Chat. Okay? Any of the, either 53 or 55, they're both a Calc Chat. 53's a Calc View. 57 or 59, they're both a Calc Chat. 61 or 63, they're both a Calc Chat. You can explore doing 65 or 67. They should both be at Calc Chat. You can do 69, it should be at Calc Chat. 71 should be at Calc Chat. 73 should be at Calc Chat. 75 should be at Calc Chat. 77, sort of an interesting problem for a few reasons. It's sort of a applying this to an actual curve that's come up in mathematics. And it's called the Lorentz curve. And one reason I stop here is mentioning that could be a paper topic right there. In fact, it could be one of several paper topics. Who in the world was Lorentz? How in the world, or why in the world, did he come up with this curve? What are some practical applications of the curve? They say here economists use it to illustrate distribution of income in a country. So this is not only a problem you can do, but it is one that could lead to a paper topic. Then there's 79, should be at Calc Chat. Oh, and 77 should be at Calc Chat. 79 should be at Calc Chat. 81 should be at Calc Chat. 83 should be, and the 83 and 85 are true-false questions. Even though you're not probably going to have many of these on a test, it's still a good thing to think through and make sure you understand why they're true or false. So that would be 83 and or 85. 87 is what they call a Putnam challenge. These are usually pretty tough little problems to do, so that's only if you want to try to tackle it. All right, any questions on that? All right, 7.1. Let's move on to 7.2, which starts here. If the PowerPoint will ever open. Yesterday afternoon, my computer just decided not to read a DVD. And it had happened once before, so I have a feeling the old computer is getting cranky in its old age. I know about that, too. Okay. All right. Here we go. Let's go from current slide. And Chapter 7 is still applications of integration. We did area between two curves. Now we're going to do volume. There are a couple of methods to do volume. The first we're going to do is called the disk method, and then we'll introduce another one that's similar to it. So we'll find the volume of a solid of revolution using the disk method, and then the one similar to it is find the volume of solid of revolution using the washer method. Okay? You just clean up the disk method. And we'll find the volume of a solid with known cross sections. Okay? That might promise to be a little more challenging, but it's all doable. Okay. So let's do the disk method first. Now, when a region in a plane is revolved around the line, the resulting solid is called a solid of revolution. Now, a region of a plane, think of area, okay? That area is revolved around an axis of revolution, creating a solid of revolution, okay? The line is called the axis of revolution. I think I just called it that, okay? Without a line, the line is called the axis of revolution. Here's one that we're going to do. Here's a rectangle. Length times width, a rectangle. The length is, they give capital R. The reason that R being the radius, later it doesn't look like a radius now, and the width is W. If you revolve that around the axis it's sitting on, that could be the x-axis or whatever, revolve that around that, you are going to, here's that rectangle, you're going to trace out, as that spins around here, a disk. Okay? That disk will have an area of pi capital R squared and a thickness of W. And that will be its volume, pi R squared W, the volume of the disk. Okay? Now that's pretty straightforward and fairly simple based on stuff not even from pre-calculus, but stuff from way in the past, if you've done any geometry and stuff like that. That's the volume of a disk. Okay? Now the simplest such solid is a right circular cylinder. So that is a very short right circular cylinder, but it is a right circular cylinder, which is formed by revolving a rectangle about an axis adjacent to one side of the rectangle. Now you don't want the axis to be here because then you double up some of that. If your axis was down here or up here, then you're going to have a hole in it. And we'll get to that later. That's going to be your washer. Okay. So this is your simple disk. Okay? And that's what we got. Any questions on that? Does it make sense? Okay. Now, volume of such a disk is the area of the disk times the width of the disk. Okay? That's what volume is. Area of the base, if it's a regular shape, times the height. Okay? And the area of that disk was pi times that. We chose to name the height of that capital R, and then the thickness of it was W. So it's pi capital R squared W. Where R is the radius of the disk, because that's what you're revolving around the axis of revolution, and W is the width. Okay? That's why we named it W. Named it R, rather than length or something like that. Now, to see how to use the volume of a disk to find the volume of a general solid of revolution that's not just a simple rectangle in cross-section, consider a solid of revolution formed by revolving a plane region, such as this one. That's definitely not a rectangle, okay? By revolving that around the indicated axis, in this case, it's going to be the x-axis. Okay? Now, what you get when you revolve this around the x-axis, like this, all the way around on the other side too, you get something that looks like a Christmas tree stand, right? Picture that? Okay? Now, not a rectangle, but you can do your little delta x's into approximate rectangles so that this would approximate, as you revolve that around, you're going to get this little, it's sort of hard to see because they don't show the interior of this. That would be the volume of this disk that approximates that little ring around the Christmas tree stand. You got some of it inside that's underestimating, some of it on the outside that's overestimating. Okay? So that's not going to be a bad approximation of this portion here that would be curving down like this. Not going to be exact, but it's going to be pretty close. Okay? Now, if you did that for delta x's from A to B, then you wind up with a bunch of disks piled on top of each other that looks like that. Not a bad approximation of this, not exact, but not a bad approximation. You've revolved it around here. So how can we make it better? That looks more like an Aztec temple or something where you have all the stairs going up it, as opposed to a smooth Christmas tree stand. The smaller and smaller delta x's. And what does that sound a lot like?
Integration.
Integration, you got it. As the delta x's are approaching 0, the summing of those disks becomes an integral. Okay? And what are we integrating? We're integrating the height of that rectangle, which is, in some sense, the value f of x of this curve here. They didn't tell us it was f of x. Let's just call that curve f of x. And it's above the x-axis, so that's going to be the height of the rectangle. So it's the integral of pi times this height is going to be your f of x squared, pi r squared, times dx. And that's it. Okay. They're going to do a little more talking than that, of course. To determine the volume of that solid, consider a representative rectangle in the plane region. When that rectangle is revolved around the axis of revolution, it generates a representative disk whose volume is delta V is pi r squared. R is the height of that disk, that little rectangle, times delta x. Just like we did before, approximating the volume of the solid by n such disk with width delta x and radius r of x of I. Okay? Now this is the ith one of those rings, okay, and the radius is the radius of that ith ring, okay? then the volume would be the summation of all those, and this would be the pi r of x of I squared times delta x. You can pull the pi outside the summation, and it would just be r of x at x of I squared times the delta x. And I think you know where we're heading here. Let's take the limit of that. That approximation appears to become better and better and better as your delta, which they call the, I always go blank on that word. By the way, we just started 7.2, which is, Chapter 7 is application of integration, 7.2 is volume of the disk method. We just started this, we're on page 455, about the middle of the page there, okay? The norm, I think, is what they call that. They don't say it anymore, but I believe they call that the norm. And the norm is the largest such interval, and as the largest such interval, the length of the largest interval, approach 0, that means your n is going to infinity. So then you can define the limit of this sum, you can think of it as Riemann sum if you want to, as the norm is approaching 0, that means n is going to infinity. The pi is on the outside, the summation of I is equal to 1 to n, but n is getting infinitely large. Your r squared, that's the radius squared times your delta x, that's going to be the area. Pi r squared is the area of the disk, and delta x is the thickness of the disk. So this then becomes pi times the integral from a to b, a is the one endpoint, b is the other endpoint, r of x squared dx. Okay? Schematically, the disk method looks like this. The volume of the disk, known pre-calculus formula, that's where they were harping on this at the end of 7.1. The volume of a disk is pi r squared w, or I would have back then been calling this a height or length or something else, but they're calling it r here, which is fine. You can call it anything you want to. The delta v would then be pi times this r is a function of x of I. That's that delta v sub I. You probably should say here this times your delta x, delta r x squared, and then you integrate both sides of this, and you get v is equal to pi. You can pull on the outside integral from a to b of r sub x squared dx. Riemann sum 1 to and integration. Okay, similar formula can be defined when the axis of revolution is vertical, revolving that way. This time, you better take your dy's, and you better have your function as a function of y. Your radius is a function of y because you're going around that way. Okay? So the disk method defines the volume of a solid of revolution by the disk method. Use one of the formulas below, either horizontal or vertical, the way you do it. Horizontal axis of revolution, going around this way. Pick your function, have your radius function as a function of your x, because you're going to be doing dx's, that's the thickness of your disk, and so you need that radius to be a function of x, and these have to be limits on x, so your volume would be pi times the integral from a to b, radius squared dx. Pi r squared is your area, dx is your thickness. Okay? If you're doing a vertical axis of revolution, then what you better do is have your radius as a function of y, not as a function of x. Okay? Because you're going to be doing dy, that's the thickness of the disk, so you need that radius as a function of y, not as a function of x. Pi r squared is still going to be the area of the face of that disk, okay? And you're going from, the limits have to be in y2, so these are going from y is equal to c to y is equal to d. Exactly the same formula, except you're substituting y's rather than x's. So, horizontal axis rotation. Here we have your function, r of x. That's your radius function here. You're going to revolve this around the x-axis. Good idea to take a dy here, a dx here. So you need this radius as a function of x, and pi r squared dx. That's going to be your thing. Pi is outside the integral, and you're going from a to b, from the lower limit to the upper limit. There you have it. If you're revolving around the y-axis, okay, then you better take the thickness of the disk to be a dy. Then you've got to have your radius function here as a function of y, not as a function of x. And your y is equal to c, the y is equal to d, those are the limits. Okay. All reinforces what we've got there. Now, admittedly, sometimes this isn't going to work very well. So in the next section, we're going to have to see how to do it when this doesn't work well. And something might work a little better. So, any questions on this? Let's do example 1. This, by the way, is on page 456. Find the volume of a solid formed by revolving the region bounded by the graph of f of x is equal to square root of sine x. And the x-axis, okay, this formed by revolving the region bounded by f of x equal to the square root of sine x, and the x-axis, and we're going from 0 to pi on the x-axis, and revolve it around the x-axis. So, if you were doing f of x equals sine x, you know that would be going, a shape like this. But when you do a square root of that, the square root is more vertical here, and flatter coming up to the maximum, still the maximum of 1. Okay? So what you get when you do that revolution is a football. Or at least it looks sort of like a football, doesn't it? Some people like to kick these things, don't they, Dawson? Okay? So yeah, you get something maybe looks a little more like a rugby ball, but I'm not sure. I've never played rugby that much. And this isn't how they build footballs either. Okay. So how in the world are we going to find that volume of that solid down there? What would you suggest we do? Let me get my pen set up. I thought I had. Oh, yeah, we went to a new section, didn't we? So what's going to be the volume of this solid? Second? Okay, and here's the radius, and here they tell you what that radius is. It's that function, square root of sine x. Okay? So yes? What? Pi times, okay, you need the integral sign, right? Then the square root of sine x, and the x is, okay, all that's inside the radical. And what you going to do with that? Square it. All right. Then multiplied by dx. All right. This isn't turning out too bad, is it? But you haven't given me where we're going from.
From 0 to pi.
Oh, from 0 to pi. Okay. Because that's the thing. You don't want to go any further, okay? You start running into some issues there. We're just going to do 0 to pi, okay? So this is going to be pi, and the integral from 0 to pi of, and what's sine squared x squared? A square root of sine x squared. Sine x dx, okay? That's going to be pi, and what's the antiderivative of sine x? Negative cosine x, evaluated from 0 to pi. Okay? So So this is going to be pi times, let's first plug in, what is negative the cosine of pi? Anyone remember that? Say again? Did you say 1? No? Okay. Cosine, remember how cosine looks? Starts at 1, goes down to 0 at pi halves, and down to minus 1 at pi. Right? Right? This is 0, pi halves, pi. So that's going to be a positive one because it's minus a minus 1, which is 1. Now we got to plug in minus a minus cosine evaluated at 0. Well, minus a minus is plus, and what's cosine of 0? Oh, I just drew it for you. I just drew it for you. Cosine of 0. This is your cosine curve. Cosine of 0 is 1. Okay. Now, this will be high-level math now from your pre-calculus days. What's 1 plus 1?
2.
All right. So we got 2 pi. There is the volume of that football, 2 pi. So when you're doing a football with those dimensions, you know you got to put 2 pi cubic whatever's of air in it. Don't we? Of course we do. Okay. Any questions? Looked like a weird thing to give us that square root, but it turned out being pretty nice since we're going to square it. And while I wasn't looking, someone snuck in, didn't you? Okay. I know you're in here somewhere. I've got to find you. Oh, there you are. Tiara. Right? Is it Tiara or Tiara?
Tiara.
Tiara. Okay. I forgot to put the symbol over it so I could remember how to pronounce it. Because I've got at least one other, either Tiara or Tiara in one of my other classes. I can't remember if y'all pronounce your names the same or different. So we're only missing Jemiah and Devin Todd came in, snuck in while I wasn't. Well, actually, I was looking. I forgot to mark it. So we're only missing Jemiah. Good attendance, folks. 1, 2, 3, 4, 5, 6, 7, 8. Yep. Good deal. Any questions on example 1? Well, let's see how they do it. Okay? From the representative rectangle that they drew there, in the upper graph of 716, you can see the radius of that solid is your f of x. Okay, your r of x is f of x. The r of x is square root of sine x. Okay, that's your r of x. And then the volume of the solid of resulting solid of revolution would be, the volume would be pi times the integral from a to b, we know that, of your r of x squared dx. That's your basic formula we came up with. So let's plug in what we know. It's going to be the pi is pi. The a was 0 and the b was pi, that you're going from 0 to pi. R of x is the square root of sine x. But we're squaring that. So that gives us pi times the integral from 0 to pi sine x dx. And the antiderivative of sine x is minus cosine x. Remember, antiderivative is opposite signs from what the derivative is. Okay? So then you evaluate that from 0 to pi. And so your pi is out here. First, minus the cosine of pi. Well, the cosine of pi is minus 1. Minus that is going to be a plus 1. Then you do minus the cosine of 0. Well, minus the cosine of 0. So minus a minus is a plus, and cosine of 0 is 1, so 1 plus 1. High-level math is 2 pi. Got it. Any questions? All right. They're skipping example 2. So let's us not do that and go back and do example 2. Make a rhyme every time. Okay, find the volume of the solid form by revolving the region bounded by the graphs of f of x is equal to 2 minus x squared. Seems like we've seen that one before, doesn't it? No, it's slightly different, okay? And g of x is equal to 1. About the line, so we're going to revolve this thing, the region is the area, I like to think of it, between f of x and g of x about the line y is equal to 1. Okay. Now they show that in the text, but since, let's see, nope, not everybody has a text, or some of you have e-text, or don't have a text. Let me draw it. Boo hiss. Okay. Okay. 2 minus x squared. Let's just do a few points there. Okay. F of x equals 2 minus x squared. When x equals 0, your function is 2, right? When x is equal to 1, your function is 1. When x is equal to minus 1, the function is 1. Okay? So it's this parabola here, and you're revolving this around the line y is equal to 1. Okay? So you're going to have the lower half of the parabola down here. Oops, that's ugly. Ugly, ugly, ugly. Like that. I got way carried away here. Okay. So basically you've got something like that. My graph isn't very good, but you get the general idea. Now that's not a circle. It's not a ball. Okay. It is the upper and lower half of a parabola. Okay. It has a little pointed at the edges here. Okay, it's not circular, not really even that close to circular. That's what we've got. Okay, when you revolve it around the axis, around y is equal to 1. Okay. Now, what's your little rectangle? Oh, before we go any further, what do you notice about this? This function and the revolved shape. What you notice about it? Maybe not from my picture, but look at the one in the book. This is what kind of function? It is a parabola. Well, when we're talking about y'all who were in here earlier. Say again? Even. This is the even function. How about this one? Really? Now 1 is odd, but the function f of x equal a constant, or g of x equal a constant, it's also even. Here's that line, isn't it? Same thing on the right-hand side as the left-hand side. This is the same thing on the left and right? The y-axis. Both of those are even functions. So, what can we do? Rather than going the points of intersection, which we already saw were -1 to +1.
Evaluate at 0.
Yeah, do it 0 to 1 and double. Yeah, you got to double it. Okay, because it's the same thing on either side of the y-axis. Okay, so let's talk about our height there. Okay, what is the height of that rectangle? This up here, remember, is 0, 2. This is 1, 1. Okay, what's the height of that rectangle? What's its upper limit? Your F. What's the lower side? Say again?
2 minus x squared?
Did you say F minus G?
Yes.
Yeah, I thought you did. Okay. All right. That is 2 minus x squared minus 1, right? Which is, this is what they're calling the R of x. I don't like to call it R of x, but that's what they're calling it. What would that be?
1 minus x.
1 minus x squared. Okay? That's the height. And your thickness, of course, is? Dx, approaching 0. Okay? And the dx sort of implies that. So what we have here is the volume will be twice, because we're only doing 0 to 1. See, we're going to, this goes from, this is minus 1, 1 here. So we're just going to do 0 to 1 in x, the x values.
We need a pi in there too.
Yes, we need a pi. I love pi. Okay, I'm glad you decided to add one. Okay, 2 times pi times 1 minus x squared squared. We got to square that radius, remember? And then we have our dx. Okay? To me, I said we got to square it. All I did was put parentheses around it. I didn't put the square. So this is 2 pi times the integral from 0 to 1. Let's square that. And what do we get? Can we square that? 1 minus 2x squared plus, second, x to the fourth. And that's what we're evaluating, taking an antiderivative of. So let's do that. 2 pi times antiderivative of 1 is x. 2x cubed. Second? 3, right? Is that what you said? Okay, I don't hear well. Okay. Plus x to the fifth divided by 5. Evaluate that from 0 to 1. All right. It's going to be a 2 pi times, what do you get when you plug in a 1? 1 minus 2/3 plus 1/5. What happens when you plug in a 0? All goes to 0. Okay, so I like doing it that way. That's why I didn't want to do it from -1 to 1. Okay, more work and not as much fun. Okay, so we got to do some calculation first. What would you do? I'll write down the 2 pi, which is, so what would that give us? 15 over 15 is 1 minus 10 over 15 is 2/3. I can't write, okay? Plus 3 over 15 is 1/5. Okay, when I add those together, the positive make it 18/15 minus 10/15 would be 2 pi times 18/15 minus 10/15 is 8/15. So that would be 16 pi 15ths. Okay? 16 over 15 is just a little bit greater than 1. multiply by something a little bit greater than 3, you're going to have something a little bit more greater than 3. So what, maybe 3.2 or 3 or something like that. Let's see what they do. They just left it as 16/15 pi. Okay. I'm happy to leave it there too. Sometimes they approximate their answers and sometimes they don't. Any questions on that? You see how it works? Okay, don't forget, you notice several things there. To square that radius, okay, pi r squared, we almost forgot that, and also the pi. Don't forget to put in the pi outside the perimeter thing. And when you can take advantage of symmetry, do it. It makes your calculations usually a lot easier. All right, that was example 2. Any questions on that? Okay, let's move on then to the washer method. Okay? We had an Italian kid live with us one school year, and my wife had a lot of difficulty teaching him the washer method, how to operate the washer. He wanted her to do all the washing, and she said, no, I'm not an Italian mom, so you're going to learn how to do the washing. Well, this is a different washer method. The disk method can be extended to cover solids of revolution with holes in them by replacing the representative disk with a representative washer instead. So what if we had this washer formed by revolving this little old rectangle similar to what we had before, but now it has 2 radii, okay? Because here's the axis of revolution down here, the rectangle is up here, okay? Well, the outer rectangle is going to be the capital R. I mean, the outer radius is the capital R. The inner radius is the little r. Okay? So what you would do is basically do one with the disk all the way down to this with a capital R, so pi r squared w, just like we did before, but then subtract out of it the disk that's in the middle. The hole in the donut, you might say. Subtract that out, and that would be minus pi little r squared times w. And that's going to give us the volume of the disk. The volume of the entire thing with the capital R minus the volume you take out the middle. Okay? So this is the procedure. Capital little r and capital R, the inner and outer radii of the washer, respectively. W is the width of the washer. Then the volume is pi r squared w minus pi little r squared w. Well, the pi and the w are the same, so pull those out, and it's just a difference in the 2 radii squared. Okay? Outer radius minus inner radius. Square of the outer radius minus square of the inner radius with your pi on the left-hand side, your w on the right. Doesn't matter what side they're on, except that's just going to be convenient to keep it that way for what we're going to do later. To see how this concept can be used to find the volume of a solid revolution, consider a region bounded by an outer radius capital R of x and an inner radius little r of x, is shown here. Okay. So what we have here is a wedge, or something like a wedge, just hanging around up here. Looks like you have a straight line as the upper limit here, and some sort of curve, perhaps a parabola down here, sort of a section of a parabola here, bounded by these 2 points of intersection there. And this you're going to revolve around whatever this axis is down here. Well, this time you're going to get they call this sort of like a frustum of a comb. That's what you would have if you just had the line there, but then the frustum of a comb has hole in it that's variable thickness because of this curve here that's going to be on the interior of it. So again, it looks a little bit like a Christmas tree stand, but it's a weird shape on the inside. Okay? So that's what you're revolving. So it would be pi times capital R squared minus little r squared times your dx, delta x, whatever you want to call that. Okay? So the region is revolved around the axis of revolution, which is a good thing to revolve around. Then the volume of the resulting solid is V is equal to, and whatever your limits were where those two curves intersected, A and B, V is pi times the integral from A to B of your outer radius squared minus the inner radius squared dx. Here was your pi, there was your w. Okay? That's why they did them this way. Hold the pi on the outside, the w is your dx, and that's going to be on the inside. Note that the integral involving the inner radius represents the volume of the hole that is subtracted from the integral involving the outer radius, which was your original disk before you subtracted the hole. So that's exactly what we have here. So here's example 3. Find the volume of the solid formed by revolving the region bounded by the graphs of y is equal to the square root of x, that's this curve, and y is equal to x squared, that's the parabola here. Okay? Now, believe it or not, the square root of x between 0 and 1 is greater than x squared. Because when you square a number less than 1, you make a smaller number. When you take the square root of a number greater than less than 1, you make a bigger number. So this is like this. This. Okay. All right. Now, and you're doing this around the x-axis. Here at the point there, it's not going to be a disc, that's going to be a washer, but that is a very thin washer, like infinitely thin. But anywhere else here, this is going to be a washer, okay, as you go further out from 0 to 1. Now, why didn't we extend past 1? Because past 1, this one is greater than this one, okay? Then you would be subtracting 1, that would work. Why didn't we extend this side of 0? This is a completely different reason. What do you call the numbers this side of 0? Negative. And can you take the square root of a negative number? No, you cannot. That's not even defined over here. Over here you can't go past because then you reverse the order of your subtraction. And here you can't do it because the first one is not even defined. The left is 0. So this is a good place to do. So let's do it. What would become of this? What would that volume be? Anybody? Anybody? Pi. Okay. Don't forget my pi. That's in between 0 and 1. Perfect, because that's where this is defined. Okay? The square root of x squared minus x squared times dx. Okay? So this will be pi times the integral from 0 to 1 of x minus x to the 4th dx. Okay? So this will be pi times x squared over 2, x to the 5th over 5, evaluated between 0 and 1. Running out of room here. That will be pi times, when you plug in a 1, what do you get? What's that? 1/2 minus 1/5. And you plug in the 0 and you get nothing. Okay? So what does this give you? Pi times what you do with that?
It'll be 3/10.
Yeah, it'll be 3/10. 5/10 minus 2/10 is 3/10. And pi times 3/10 would be 3 pi over 10. I sure hope. Yeah, that's what they got to. Good for them. Any questions on that? Let's see how they do it. From that you can see the outer and the inner radius. The outer radius is your square root function because it's on top, between 0 and 1 anyway. And your inner radius is your parabola, which is x squared. Okay, integrating between 0 and 1, your formula being pi times the integral of your outer radius squared minus inner radius squared times dx will be pi times the integral from 0 to 1 of the square root of x squared minus x squared squared, and that gives you pi times the integral from 0 to 1 of x minus x to the fourth, just like y'all got. Then when you do your integration, that's the easy part, isn't it? Setting up the problem is the hard part. Integration is usually the easy part. The calculus is the easy part. Pi times x squared over 2 minus x fifth over 5, evaluated from 0 to 1. And they don't show any of the details, just say it's 3 pi over 10. Which, by the way, pi is just a little bit greater than 3. So this will, 3 times that will be something a little bit greater than 9 over 10. So it's something just less than 1. Okay. Not that you need to know that. All right. Any questions? In each example so far, the axis of revolution has been horizontal, and you've integrated with respect to x. In this next example coming up, example 4, the axis of revolution is vertical, and you integrate with respect to y, so that means you have to have the function as a function of y rather than a function of x. In this example, you need 2 separate integrals to compute the volume. Not because it's y, but just because of the nature of the problem. Okay. So here's example 4. Find the volume of the solid formed by revolving the region bounded by the graphs of y is equal to x squared plus 1. There that is. That's going to be your good old parent function, y is equal to x squared. That would be down here. You elevate it by 1, so it's up there. Y is equal to 0, so that's going to be your x-axis. X equals 0 is going to be your y-axis, and x equals 1 is going to chop it off over here. And you're going to revolve that around the y-axis. Okay? Now, I'm probably showing you too much here, but can't help but be showing it. Okay? This gives you a disc base with a washer on top, right? Because up here you've got a hole in there. Okay? This part in here is washer in nature. Every sliver here is like a washer. Slivers here are like this. So that's why you have to do 2 pieces here. Okay? From 0 to 1, your outer radius is 1, your inner radius is 0. You just got a disc there. Okay? For the part from 1 to 2, then your outer radius again is 1, just like before, but your inner radius is this value here, which is now. Remember, we've got to get this in terms of y, not in terms of x. So that's the first thing we do, is solve this for x, not for y. They gave it to us in terms of y, you need it in terms of x. So what we're going to do is subtract 1 from both sides, and that gives us a y minus 1 is equal to x squared. Okay? And then what do we need to do? To solve for x. Square root of square root with both sides. So you get x is equal to the square root of y minus 1. Now, notice your x's here. Now, technically we should have said plus or minus, shouldn't we? Take square root of both sides, you should. But notice here your x's are always positive. So we just leave it positive square root of y minus 1. We're not doing anything to the left over here, so we're just going to square root of y minus 1. So that's where they got this. Your inner radius up here is going to be the square root of y minus 1. That's that curve right there. Okay? So, let's do the volume. What would it be? Which you want to do first? The base or the upper part? I really don't care much. The base, okay? So what is the volume of the base going to be? Help me out here. Pi, good. Second? The integral from 0 to 1. One. Okay, now, second.
I was saying the square root of y minus 1. 1 squared.
1 squared. Okay, that's what I thought I kept hearing people say. What's your D?
dy.
Ah, it's a dy. Guess what? It's not going to give you a different answer to do this, but because you're integrating with 1. So this will be what? Okay, that'll be, okay, it'll be pi times, if you do that, you get y. Y evaluated from 0 to 1 would be y. Okay. I mean, it would be 1. Okay. So it's just pi. Enough of that is pi. Okay. All right. Now let's do the upper part. The looks kind of like a dog bowl up there, doesn't it? You know, if you just did that part. Okay, so let's do V of the dog bowl. Okay. What would that be? Pi times the integral from 0 to 1. Wait. Your integral is always going, yes, 1 to 2. It always goes by what your D is, and your D here is y, so it's y is equal to 1 to y is equal to 2. Okay? Continue.
Square root of y minus 1 squared.
Okay? Say that one more time.
Square root of y minus 1 squared.
Okay, that's certainly in there, but there's something else in there too.
Then 1 squared.
You got 1 squared. That's from your outer one. Minus, as you said, the square root of y minus 1 squared dy, because you got a dy there. Okay? So let's do that. V of the dog bowl, that's not what the book calls it, is pi times, let's carry this one more step, times 1 to 2 of 1 minus, and what is square root of 1 y minus 1 squared? y minus 1. Okay, dy. Okay, so that will be v of the dog bowl would be pi maybe I should do one more step. Okay, or 2 minus pi, right? 2 minus y, I'm sorry. Got pi on the brain. Yeah, what I was going to do is erase this. Oh, what are you doing here, folks? It's supposed to be erasing. Erasing. Okay, there we go. All right, let's get the pen back. Integral from 1 to 2 of, what did you say? 2 minus y dy. Okay, so this will be pi times antiderivative of 2 minus 1. 2 minus y. Help me. 2y, right? Minus what? Y squared over 2, evaluated between 1 and 2. So this will be pi times what? Plug in the 2 first and you get, help me, 4 minus what? Minus 2, is that what you said? That's when you plug in the 2. Then you do a minus, and what you get when you plug in a 1? 2 minus 1/2. Okay. I'm running out of room rapidly, so let me see if I can write this out. Oh, let's see if I can. Pi times 4 minus 2 is 2, minus 2. Huh. That's interesting, isn't it? Okay. And then minus a minus 1/2 is plus 1/2. So I get pi over 2. Is that right? Yes. Okay. Then you add it to the base, and you get pi plus pi over 2 is how much? 3 pi over 2. 3/2 pi. Okay. Yes, that's what they got. Let's see how they did it. Okay. For the region shown, the outer radius is simply capital R is equal to 1 for the whole thing. There is, however, no convenient formula that represents the inner radius. So split it into 2 pieces. When y is between 0 and 1, then the inner radius is 0. Okay? But when it's between 1 and 2, then it's determined by this equation here, which implies that your x is equal to, or x squared is equal to y minus 1, x equal to the square root of y minus 1. We only use the positive part because of our original definition that x's are always greater than 0. Okay? So, there's your inner radius for the upper part. So your radius function as a function of y is 0 when you're in between 0 and 1, and square root of y minus 1 when you're between 1 and 2. Okay. I'm not super sure that expressing as a piecewise defined function is going to be the easiest way to see it, but it's certainly true. Okay, using that definition of the inner radius, you could use the 2 integrals to find the volume. The first of these is going to be pi times the integral from 0 to 1. That's where your y's are going. You're doing dy, so you always measure this with y. And it's 1 squared minus 0 squared. Because that was your outer radius, inner radius. So that first 0 to 1. That's a piece of cake, pi. Okay, this gives you 1, dy, integrate that, you get y. 0 to 1, you get y. Now you get 1 times pi. Okay. But this one, the pi going from 1 to 2 of 1 squared, is the outer radius minus the inner radius squared, which is, we've only integrated this, or not integrated it yet. Squared 1 and subtracted 0 from it, you get 1. Okay, and here you get 1 minus y minus 1. Well, 1 minus y plus 1, so 2 minus y, dy. That's what you're integrating there. This gives you really simple. Antiderivative of 1 is y. Evaluate that from 0 to 1. Antiderivative of 2 minus y is 2y minus y squared over 2, just like y'all did. Pi in front of that. And this gives you pi, which we had already done. This gives you pi times 4 minus 2 plus 1/2. Now, that's correct, but they didn't show you how they got it. But these three add to 0, and it just gives you 1/2 pi. So pi plus half a pi is 3/2 of a pi. 3 pi over 2. Make sense? All right. Notice that the first integral represents the volume of a right circular cylinder of radius 1 and height 1. We could have just done that. Okay? Pi times 1 squared times 1. That's just pi. Okay? You didn't have to do the integral of that. That portion of the volume could have been determined without using calculus. Very true. Oh. Okay, that was example 4. Goodness, I'm hungry. Okay. What's that? I can't hear you.
We have 12 minutes.
12 minutes left, so you think I can make it, not pass out from hunger? Okay. I hope so. We'll see. Okay. Thank you for keeping up with the time there, too. Okay. I guess that figure at the bottom of the page that goes with the technology, I'm not particularly moved by it, so I'm not going to fiddle much with it. This is the bottom half of 459, so they've skipped example 5. Now the question is, can we do example 5 in the little bit of time we have left? We hope so. I can't get my pen. Okay, there it goes. Okay. Now, one good thing about example 5 is you can go to larsoncalculus.com and see an interactive version of this type of example. So here's what we got. A manufacturer drills a hole through the center of a metal sphere of radius 5 inches. So here is your metal sphere. Now, that's not a very good looking sphere. Okay. There's a metal sphere. Radius 5 inches. Okay. All right. From center to anywhere on the sphere. Okay. He drills a hole through the center of this metal sphere of radius 5 inches, as shown in the figure here, which they don't show us. Thank you for making me draw it myself. The hole has a radius of 3 inches. So we're drilling, and they're showing a horizontal hole. I'm just going to pick something about like this, and basically we're getting rid of this part here. Okay, so all this is disappearing. So what we've got left is this point up here. Now, what they do wisely is set the center of the sphere at the origin. Okay? Now, let's take this radius here of 5 that goes to this place where this ends, and we know this is 3 here. Okay? And that's the 5 up there. Okay, before we do any more, by taking this orientation, which looks like it's going to be the better deal? Doing dx's or dy's? Ah, for sure. Thank you for saying dx's. So we're going to be taking this is going to be our little rectangles, okay? And it's from the edge of the sphere to that cylinder. Hey, I know that's going to be radius 3, right? They did say radius, yeah. 3. So I know the little radius of this is always going to be 3, okay? What I've got to get is what the upper radius is going to be, and it's that portion of your big sphere. Okay? Well, if this is 5 and this is 3, what is the horizontal length here? Know what I'm saying? Asking. What is your x going to? If you're choosing a dx, you got to have boundaries on the x. So x is going to go, and guess what else? By choosing that as the origin, what can we do? Yes, go from 0 to whatever you go out here and double, because this over here is exactly the same as that. As long as you have uniform density and stuff like that, which no reason to expect otherwise. So what we have to do is get this outer limit. If we got that, we've got this thing pretty well knocked, I think. Okay? So what do we have here? What is that outer limit on your x? It doesn't go out to 5, because you cut that hole out. Where does it go to? 4.5? Is that a guess or a calculation? Yes. I thought so. Okay. Okay. You know the vertical here is 3. This distance here is 5. How do we determine the horizontal? Pythagorean theorem. What does that tell us?
It's going to be 4.
It'll be what?
It's going to be 4.
4. All right, good. Because this is a good old 3, 4, 5 triangle, right? So this is going to be 4 on the x. So we know where our limit is going to be now. So what do we have here? The upper part here is going to be a circle of radius 5. So that's going to be what's the equation of this circle here?
X squared plus y squared equals.
Okay. All right. You're saying x squared plus y squared is equal to, what did you say? 25. Okay. So then you're doing dx's, so we want to solve for x. So y squared is equal to 25 minus x squared, right? So y is equal to, help me somebody, the square root of 25 minus x squared. Okay. And since we're taking the upper up here, we're going to have y positive. You don't have to do plus or minus. Okay. So that's going to be the outer radius. This is our capital R. What's our inner radius? 3. Excellent. Okay. So I think we're ready to go. The volume of the thing remaining here is going to be what? 2 pi, excellent. 2 because we're only doing a half of it. Integral from 0 to 4, excellent. Okay.
Square root of 25 minus x squared squared.
Okay, which would be
Just 25 minus x squared.
25 minus x squared,
Minus 3 squared.
which is 9. Look at that, and then dx. There's your thickness. I think we got it, don't we, Houston? Okay, what does this give us? V is equal to 2 pi times the integral from 0 to 4 of 16 minus x squared dx. And what would that be? 2 pi times 16x x cubed over 3, evaluated from 0 to 4. This is the hard part, okay? The calculus was the easy part. 2 pi times 16 times 4. 64 minus 64 thirds. Okay? And I'll do the 0 part, done. Okay? So this is 2 pi times. Now, here's how I do this problem. It's a little bizarre. Factor out the 64, you have 1 minus 1/3, right? So that's 2/3. So it's 64 times 2/3, right? Okay, that's a lot easier than doing least common denominators and stuff like that.
128.
Okay,
Is inside parentheses.
did you multiply? Okay, you got to double it again. 256 pi thirds. I think, yes, therefore I am. Okay, yes, it works. 256 pi thirds. All right. How are we doing on time? Huh? 2 minutes left? I don't think we're going to be able to do the solids with known cross-section in that 2 minutes. So we'll begin there next time. If I can find me a pencil here. There we go. Okay. Put that in place. And, oh, we came so close to finishing. Homework exercises here will be either 5 or 7. They're both at Calc Chat. 5's at Calc View. Do either 9 or 11. They're both at Calc Chat. 9's at Calc View. Either 13 or 15, they're both at Calc Chat. 13's at Calc View. Either 17 or 19, they're both at Calc Chat. 17's at Calc View. Either 21 or 23, they're both at Calc Chat. 23's at Calc View. Any of the odds 25 to 31, they're all at Calc Chat. 33 or 35, they're both at Calc Chat. 37 or 39, they're both at Calc Chat, with 37 being at Calc View. 41 to 47, any of those odds are all at Calc Chat. Okay. I think you can do 49 or 51. I was trying to see where this new part we have is solids with known cross sections. I may have gone too far. Do as many of those as you can without getting to the solids with known cross section. We'll pick up from there and go. Okay? That wasn't very specific, but I think you'll know sense where to stop there. All right. Any questions? Good. Good deal. Oh, and y'all did get the word on the good news, bad news situation, right? The good news is Monday is Labor Day, so it's a holiday. The bad news is that means we won't be meeting Monday. So, get over it. Okay. But live through it. We'll see you next Wednesday. in 1 week. All right, let me end.